Welcome everybody. Hello. We have today Professor Noah Finkelstein as our guest speaker. He did his undergraduate work at Yale University in mathematics, for the mathematicians here. He then worked in industry in a couple of companies. After that, he joined the Laboratory of Comparative Human Cognition at the University of California, San Diego, where he studied the early stages of email communities and networks. Then he went back to school to Princeton University, where he got his PhD in applied physics. And after that, he did a postdoctoral fellowship studying how people learn physics. Now he's here at the Department of Physics, and he serves as one of the principal investigators at the Physics Education Research Group. That's the PERC. Investigates in STEM education, the Integrative STEM Education Initiative. He received many awards, a couple of them that I'd like to remark is the Boulder Faculty Assembly Campus-Wide Award for Excellence in Teaching, and more recently, the University of Colorado System-Wide Diversity and Excellence Award. So,
thank you. Hey, it's a real pleasure to be here. Now, in thinking about this IGERT community, I think that my background maybe very well suits this. So, did some work in mathematics early on. I worked in industry at Ford Aerospace, and as soon as I quit, they sold the company to the French. So, I don't want to take credit for that, but so begins the demise of the U.S. aerospace industry. But then really focused back at the university in education. Then I did my work in applied physics and laser physics and optical imaging. And I subsequently then really formally engaged in education work during my postdoc. So in some sense, this embodies sort of a nice history and trajectory to bring me to talk to you all about COSI. And I'm happy to talk to you about that perspective as you wish. I think this is a great opportunity for us to talk about education within this community and as well, and particularly for the grad students among us, about the opportunities, the landscape that sits before you, where you might get involved and how you might think about education and participate. And so but I'm also open, so I'm happy to take suggestions or feedback from you all. I'm happy to talk more about me. I'm happy to talk more about my research. I will provide a little bit of sort of framing comments, but then quickly ask you what it is that you want to talk about. Is that all right? Is there anything that's burning on your mind that you want to learn about right now that before, it's unusual for a seminar or a colloquium, I guess, to ask if there are any questions before the speech, but sure?
You should only present your IGERT program and how it's with your work and how it's organized.
Okay, I'm happy to talk about it. I don't have an IGERT program. I have a large research group in physics education. We have many graduate students there, and more recently we have a program called iSTEM, which is integrating STEM, and that's across campus, and it's a campus-wide initiative. I'll be pleased to talk about some of that. And I consult on this. IGERT helped write the proposal. So you can thank me with cookies later. Oh, and those who don't get cookies, I didn't see many of you over at the cookie hour, but I strongly recommend the informal cookie and coffee hour. That's from 3:15 to 3:45, all the way over in engineering. Okay, but thank you. I will talk a little bit about that. So this is going to be a talk about how is it that we might make a scholarship out of education and apply the same sort of scholarly inquiry into science, technology, engineering, and math, STEM education, as we do into our other intellectual pursuits. How is it that we can be scholarly about our teaching and reflective about our teaching and build on prior work as we do our engineering research or science research or math research along the way. I'm going to talk a little bit about that. And we have a really sort of unique opportunity right now, which is we're building this program, this particular IGERT program. This is the, we're 1.5 years into this or so, I guess. So this is going to go on forever, and I'm sure going to be renewed. In fact, in the latest legislation that, interestingly enough, I've been asked to work on, they're talking about increasing the IGERT funding at NSF. So, so maybe that is good news for the future. But as we sort of think about this and think about sort of the, scholarship in all educational endeavors, one of the important things that goes on within this COSI IGERT is evaluation. And I wanted to introduce Dr. Stephanie Chastain, who's the evaluator for this project, and I work closely with her both in the design of this and also in the evaluation. So let me turn it over to Stephanie.
So I'm just taking this chance to kind of hijack and talk for just a couple of minutes because I wanted to have the people who are part of IGERT get a chance to actually see me in person because I'm going to be talking to you in a lot of depth over the coming years. So I'm an external evaluator, which means that I'm external to this program, and all of the evaluation I do on the program is I am a neutral party, as it were, and anything that you tell me, this is just for the people who are actually in the IGERT, anything that you tell me is going to be held completely confidential or anonymous if you wish to give me anonymous feedback. I'm in the physics department, but my work in the physics department and the physics education research group does not relate at all to the IGERT. I'm the one who sent you a survey back in December, both to faculty and to students, and thanks very much to everybody for filling that out. If you ever have any questions, comments, concerns, you are interested in how any of that information is being used, please contact me. You'll be in contact with me quite a bit over your graduate career if you're a student in the IGERT. And lastly, I'll be contacting each of you this summer to set up individual interviews for those that I haven't already interviewed, so you can expect to be getting some more emails from me. So that's all. We just wanted to let you know a little bit about what the evaluation is and who I am, so you could see me in person and understand that this is something that's important for the program, to give feedback to the program, and it can also be important for you. I was a part of an innovative postdoctoral program when I was a postdoc at the Exploratorium Museum of Science, and I actually really enjoyed talking to my evaluators because the questions that they asked me gave me a lot of insight into my own progression through that program. So hopefully participating in the evaluation can not just help the program, but also give you some insight into your own experience. So that's all, and my email is stephanie.chastain@colorado.edu if you ever want to contact me.
All right.
Thanks, Noah.
Thank you, Stephanie. So, right, let me underscore that, I mean, you are the ones helping build this program. And if it's not for your success in the lab or whatever you mathematicians do on the piece of paper, you know, this program won't be considered a success. Similarly, you have opportunity to shape what it is that goes on here in this program by providing this formative feedback to form what it is that COSI becomes. And we wholly expect this to outlast the initial funding that goes on. So with that, let me turn an eye towards being scholarly about teaching and learning in science and engineering. So as Ariel mentioned, I'm part of a large research group here that spans between the physics department. We have 5 faculty in the physics department, and then also Valerie Otero is a professor in the School of Education who's part of our research group. We have a large number of postdoctoral researchers and scientists in our group, a big staff, and grad students that span. In fact, great to see Maylee here. So, I'll also say that we're the largest research group of its kind in the country, and for that we need a lot of money. We bring in a gaggle of money in order to run this operation. And I'll tell you a little bit about what it is that we do, but I'm happy to chat about what does it mean to conduct research. Well, I want to talk just a little bit about a survey of physics education research as an avenue to say what is it that's known from within a disciplinary field, in my case physics, about education, and why is it that we think about that. I'll talk a little bit about the implications of that, a little bit of theoretical basis, some sample applications as you're interested, and ways to be involved for you all. Hi, Lucy. So, I mean, one of the really exciting things is you might say, golly, education, that's a really important thing to do, and it's, you know, there's, you know, just like healthcare, it's right up there in the political arena, but physics? Why a physics department? And one of the things that I find pretty impressive is that in the tree of departmental activities, which I did not construct, it is now physics education research is listed as one of the staple activities like nuclear physics, our optics initiative, high energy, and the rest of it. And so that's really nice that we are a subgroup of the physics department, and in fact nationally the American Physical Society has said this is something that physicists do. This is a part of doing physics. Now, which is fascinating. We can talk about what that means to have disciplinary-based education researchers, and why is it that that is helpful or troublesome. This is the number of tenure-line faculty assigned in the group, turns out. But in the physics department. So a few take-home messages of things that we've learned when it comes to, one of the nice messages is that the applied side of physics education research is improved teaching and hopefully improved learning for our students, we would say. And so there's some take-home messages that I'll begin with right off the bat, which is when we think about education and educational practice, that actively engaging students and ourselves as learners is critical. That what people know affects what they learn, and that contexts shape what students learn, both in terms of content and beliefs. And I'll sort of unpack what this means along the way. Here's our first opportunity. Do you want to learn more about the national scene here about physics education or education generally?
Yes.
Yes. Okay. Well then, all right, you asked for it. How important is education? Pretty important? It's up there. It's on the list. It's about this important. What's interesting is that there's a fair amount of national rhetoric about this that we find here. This is impressive to me. Newt Gingrich, formerly Speaker of the House, famed for his Contract for America, potential presidential candidate in the next round. He's now at the American Enterprise Institute. It's a think tank. It says the crisis in scientific research and education is the second greatest threat facing American national security. Only a nuclear or biological weapon released in an American city is a greater threat. Well, that's pretty strong rhetoric. In terms of national security, it's a national security issue. Education is number 2. Who would have thought you talk about national security as the reason for education? Somewhat fascinating. What are other reasons that we might want to invest in education in our society?
Economic.
Yeah, workforce development. If you're a politician, the 3 most important things to get elected: jobs, 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 right? How do you get jobs? You have an educated citizenry. And we could talk about democracy being based on an educated citizenry. So this is fascinating to me. You might ask, what is our goal here? In the United States, I love this. There's a statement made here by the year 2000. This is a little bit dated now. The United States will be first in the world in mathematics and science achievement. This is particularly focused on K-12. There's a good news, bad news part to the statement. The good news is this at least was made before 2000. Okay. The bad news is this is actually law. And you might ask, where does this come from? Why do we do this? And we were talking a little bit. You might actually look at how the United States is doing, particularly in K-12 education. But we'll turn to college education in a moment, which may interest us. But we actually all have a role in K-12 education, not only as having been educated there ourselves, but we get to set the stage. And we can all argue why it is that, in fact, engineering education happens to be really on the horizon in the national dialogue for K-12. That this is, in fact, what children do naturally in terms of science. They're not scientists naturally. They're engineers naturally, which is fascinating to me. We might talk about the distinction there. And mathematicians, sorry. It's true, everybody counts. So here's a study from 1995, although it's been replicated in the last 15 years, time again and time again. This is average physics performance for advanced science students. These are our AP students in the United States. Okay, and IB students. How do they fit internationally? Outperforming exactly no other countries in this international sample. In fact, if you look at how we're doing in terms of science here, this is the National Assessment of Educational Progress here, and you take this forward to see if we actually broke the law or not. From 96 to 2000, those data were 95 before. This is a fraction of Americans. They're 21% proficient and above. That's where I would set like a minimum bar if you look at what the language of what proficient means. It only means having a partial mastery of the topic. It's stunning to me. That's not basic, that's proficient. Okay? 21% have proficient or above, and we carry that forward. The only statistical difference from 96 to 2000 is that there are more folks in the bottom rung here at below basic, yet fewer students. So no surprise, but the top 1% of U.S. students fit in the international top 7%. Per capita, there are 7 times many more students in Europe who are learning science than there are in the United States. But certainly college couldn't be that. We have the best educational system in the world in college. So, at least this is what my colleague Eric Mazur at Harvard University said. So on his midterm, he gave his students the following question, which is to say, calculate the current in the 2 ohm resistor here, which I guess is here on this fancy circuit. I'm sure you electrical engineers have already figured it out. I'll ask you the answer in a moment. And on a few questions later on the same midterm exam, he asked, all right, what happens to the intensities of light bulbs A and B when the following switch is closed? Right. So these are the 2 questions they asked on the same midterm. And how do you suppose students did? Well, I mean, first off, which is the harder question? This question or this question? First one. All right? First one you have to compute, for instance.
I would say the second one is, because anybody can divide and multiply.
Ah.
So you have to actually think to answer the other one a little bit.
Aha. Well, it depends what you mean by thinking, and it also sounds like you're... But you're right, and that's I wholly attribute that to your wife. So in fact, if we call this the conventional problem, this one is much more like you would see in your standard freshman or sophomore level course, right? Much less likely to ask. Because certainly if somebody's able to calculate the current, then they're able to calculate the power dissipated. Because it's current times voltage, right? And that's brightness. So one means if you do one well, you know that you're going to be doing the other. But in fact, students scored 69% correct on the conceptual. The same students scored 49% on the conventional problem. Which suggests that, right, it's opposite of what we would have expected. This problem is in fact the harder problem. This conceptual one, with no calculation required, is the harder one. The thought was, if you can turn the crank, you know what that means. But in fact, the hard part is knowing what that means. In fact, the story gets a little bit more complicated. If you look at how, since you have individual students engaged in, sorry about this, but I didn't put the projector here. This is what happens in business. So since the same students are solving these 2 problems, you can plot their performance on one problem, the conventional problem, versus the other problem, the conceptual problem. And there are 2 things to notice. First off is, what's the correlation? Right? Not such a strong correlation. You're like all over the map here, with the exception of one area. What area is not particularly well filled in? You got it. Thank you for, this is my standard teaching technique. Whatever, you're right, okay. But this area, I'm sure that's what you're pointing to, right? And, because you're brilliant, which means that I'm a good teacher. So, but the point over here is they're not so well filled in. What is this area? This area means that you do really well on the conceptual problem, but not well on the conventional problem. So if you do really well on the conceptual problem, you're not going to bomb out totally on the conventional problem. You're at least over here doing somewhat well on the conventional problem, where students can turn the crank over here, calculate the current, and have no idea what current represents. So you can get 100% on the conventional problem and not be able to tell me what it means.
Can I ask a question about that?
Yeah, sure.
Does that mean, is that an indication of teaching just to a test rather than?
Yeah, I don't know what teaching to a test means. This is a phrase that's brought up all the time. It does mean this tells you what the goals are, presumably in a class, that the goals have not included a focus on the conceptual underpinnings. Certainly we haven't held students accountable for doing this. It's very unusual. This is why such a problem like this looks unusual to us, and it's only in the last decade or so that these problems have started appearing, at least in introductory physics courses. Right. So in that sense, yes. So interestingly enough, to stay at the national scale, and I'll move on rapidly here, such findings as this were somewhat disturbing to folks in Congress, which I find amazing. But in 2005, long about that time you got the Newt Gingrich quote, right? Congress charged the national academies, the Center for Smart People, National Academy of Engineering, National Academy of Sciences, and National Institute of Health, to come up with 10 action items in priority order that are designed to enhance science, technology, engineering, and math so the U.S. can compete, prosper, and be secure. I think that's actually really interesting to unpack this, to say, what's the national dialogue about? Why do we want, what is our society about? How is it that we invest? To what ends? What are our goals as a society? Okay? Competition, prosperity, okay, security. So, of course, this being the Center for Smart People, they came back with 4 recommendations. In priority order, okay, 10,000 teachers, 10 million minds. Number 1 focus was on K-12 education. Why would that be? Okay, too late to catch him as a freshman. It's actually partly true, although we can talk about remediation. We do actually a tremendous amount of that, but you're right. Yeah.
You want non-scientist professionals to still have some working knowledge of science and the average citizen.
Right. And I'm going to zoom back one level. I mean, education is a fundamental form of investment in the future of our society. And K-10 education, at least, is mandated. Right? And most folks, I mean, 80% of the jobs that are going to be coming out require a college degree with some level of competence in technology, according to the Department of Labor. Okay, so, and then the next item here is in basic science and engineering research. And then the third item here, that's you all, the best and brightest in science and engineering education, higher education. Fundamental form of investment in the future of STEM itself, science, technology, engineering, and math. I think really clever. So impressively, actually, this is now law. Now, we know what laws get us, right? We saw the last law. But I'm actually very pleased with this. In fact, I just worked on currently this is in the midst of reauthorization, and there's talk about, this is where I mentioned, there's talk about increasing the IGERT funding, and as well as GRFs and other areas in the current reauthorization of this that's going on right now. So, so let's take a look and unpack a little bit more about what's happening at undergraduate education, shall we? Well, I'll talk about PER in a moment. So you saw this conceptual question that we saw before. An early sort of litmus test was this force concept inventory. You have a ball, I'm sorry about the lousy quality of this print. You have a ball that enters a track, you're looking down at a table, point 1, the ball follows the track, which way does it follow, right? Sort of an unusual question to be asking our students. Maybe not unusual now, but certainly a decade ago, and when this was first issued was, it was issued 15 years ago for the first time, maybe a little bit longer, and actually 86. Wow. So the correct answer is B, but about a third of the students say that it's A, a third say that it's B, and a third say that it's C, D, or E. Interestingly enough, you teach the students in class, you show them a demonstration, you ask them if they saw the demonstration of the ball going in the loop, and they say yes, and I remember, it's just like I answered, it keeps going in the direction it's following, and it keeps followed A. I remember that distinctly from class. This is a product of our show and tell educational system. The idea that you can direct information to students. So there are 35 questions of this nature, and you can ask this both before instruction, is what students know coming in, after instruction, and call the difference learning, post minus pre, whatever happened in the middle. And then you want to be able to compare places where they don't learn a lot, like Harvard, with places where they do learn a lot, like Colorado. And so you have to normalize it. So how much did you learn out of what you could have learned? And then this is a normalized scale from 0 to 1. And this was a famed study now from '98, 6,000 students across 40-some different institutions here. And the take-home message here, you'll notice nobody breaks 30%. take-home message is students learn about 25% of the most basic concepts that they didn't already know coming into their classes in physics. That's state of the art. I'll talk a little bit about that. So that's one form of measurement. Are they learning these concepts? That might not be the only thing we care about. We teach a lot of other things. We certainly teach that algorithmic problem solving. We also teach about attitudes and beliefs. What do I mean by attitudes and beliefs? Well, I can ask students about the nature of physics or the nature of science and engineering and the nature of learning physics or science and engineering. And this has been referred to as the hidden curriculum. Why? Because we often don't teach people about this explicitly, but by giving people a multiple choice test, you send a message about what the nature of knowledge is. That there's one of 5 possible answers, that it's already known in advance, that it should take you about a minute to solve that problem. All right, so that sends all kinds of messages about what the nature of knowing is in our classes, say in physics. I mean, there's a reason to do multiple choice tests, but you can ask students to, it's a very simple approach. You ask students to agree or disagree with the following statements, like, I study physics to learn knowledge that will be useful in life. Is physics relevant to me? Or the nature of learning physics. In order to learn physics, I need only memorize solutions to sample problems. Is that the way we learn? And so we have actually a variety of different categories here, 8 different categories in this Colorado Learning Attitudes About Science survey that was developed as part of Wendy Adams' thesis with our research group. How connected is physics or science to the real world? How interested are you? All the way down to what's the nature of science and your confidence and ability to engage. Now, you might say, hey, we don't teach this in our class, it's hidden, and these are big ideas, like personal identity is a big idea, so you wouldn't expect to impact that over the course of a semester. So good news, bad news scenario again. Good news is we do impact students' beliefs over the course of the semester, and the bad news is they're fairly detrimental. So the shifts out of 100% from beginning to the end of semester are invariably negative, okay? Sometimes double digits so. So students come out of my physics class thinking that physics has less to do with the real world than when they entered the class, and I taught them that. And the problem is, physics is a study of the world around us, except in our classes. There are some other things that are mildly disconcerting. This is for a class where students learn a lot on those conceptual surveys. This is high learning gains. So I'll talk a little bit about that. So engineers, less personally interested in our physics class than other majors come in. Or for the few students who are physics majors, you can actually take a look at their problem-solving confidence. There's a huge gender disparity. For the physics majors, the males become somewhat more confident, and the females much less confident in the introductory sequence. This has led to an entire line of research on gender gaps and gender disparity in the physics department. So we might then ask, what's the model? Why does this happen? What's the nature of why this happens? And the answer is, we have a model of our educational system. We're enacting certain sorts of practices that fit in a fairly well-honed model that's been around for a long time, which is that you can take some kind of content and through instruction transmit ideas to individuals. And this is dubbed the transmissionist model of education. People have known about it and talked about it for a long time. There have been educational scholars who have created diagrams about it. This is one of my favorite educational schematics. It actually conveys a tremendous amount of meaning about the nature. We assume that students are empty. We fill them up. All right? They have no idea what's going on. That they're passive in this process. Right? And this is a fairly easy, and they're on a conveyor belt. It's a fairly easy thing to debunk, and yet it's built into our classrooms. This might have been your physics classroom in Stanford, actually. There's a picture from Stanford. And so you might ask, actually, where does this, this is built into the structure of our classrooms. This classroom is sort of designed for me to be transmitting information to you. And we'll sort of pause and ask, is that really what I'm doing? So you might ask, where does this come from? Interestingly enough, there are models of this from 5,000 years ago, when people were learning, scribes were learning cuneiform, and these were bench seats, and they had little clay tablets that they were doodling on, actually not paying attention. Feynman says you can't teach that way. I think that it's hopeless lectures on a big scale. I mean, what's interesting, I emphasize that we know more than Feynman did in this sense because he only thought that, and we can demonstrate it now, that this is a failed model. So what we know, actually, both from psychology and cognitive science and learning sciences and then research that we've done within the disciplines, is that there's got to be an active construction of content that you've got to internalize based on what you already know coming into a classroom. And this is, for those people who care about the jargon, it's called constructivist, this idea that you can build on prior ideas here in particular ways. So I'll sort of talk about this just a little bit, but this sort of has led to this point that actively engaging students is important, that you have to be active in the process. And for all of those, who know about clickers, that's in fact some of the toy models, I guess I would say, about learning that have led to the importance of things like peer instruction and the use of clickers, where I stop a lecture every so often. I ask students, are you following me on this sort of, I was teaching about lasers one day, and what can happen with, excited state atoms and ground state atoms. Here, and I ask the class, and I find that, more than half the class got it right, so I just move on. Well, it depends on what your goals are, of course, in a class. But the point is that this provides an opportunity for students. I mean, I quip, but I teach 600 students at once in the large-scale introductory physics classes, and the running joke is that because we care about student learning, we break that into 2 sections. But the truth of the matter is, in those 300 student sections, every single student in my class not only has a voice, but I demand to hear from every one of those students. And the only way I can do that is limit their bandwidth, so their bandwidth is A, B, C, D, or E. Right? So, but I can process that very quickly with a computer, and that gives me feedback. But it also then becomes a tool which I can reorganize the social pattern, where you can stop and talk to your neighbor and justify. You've just voted, now you're invested in an answer. You can pause and engage and justify. That's the active part, where you're processing and reasoning and justifying what's going on and why it's really important in a classroom. Now, this is another point that we often don't take into account, that we sit there and when we teach, we think the big thoughts about how is this field constructed, what's the fundamental nature of this field. This is why the Feynman lectures are terrible unless you already know physics, in which case they're great. All right? So they're just a beautiful organization of this discipline, but aren't based on what it is that students know coming into the classroom. How is it they are going to build on what it is that they know in order to make sense of what's coming on. And I've got an example here for you. This is an analogy. But here's a little cognitive task. We've been talking for a while. So I'm going to let you do some work. Try to memorize the following number in order, please. Maybe you've seen this. The number is 3732371945530017. Okay? Now, the number again is 3732371945530017. The reason I know that is this is my credit card number, so if that gives you incentive, okay, you can sort of go ahead and memorize that. I'll give you a moment. Now, you've had an opportunity to memorize that, and if I were really mean, I would do something else now and tell you my phone number. My office number is 303-735. If you have any questions, so I'm on the 10th floor of the physics tower, F1021. Okay. If you have a piece of paper or a pen, you can go ahead and try and write it down now. Okay, so how many numbers did you get? Number was 3732371945530017. Got all of them? Okay, is that because you used some sort of cognitive tool like a pencil? Oh, okay, nice. All right, how many of you got, 5 or so? It's okay.
Can you give us the last 3, the numbers that are on the back?
Okay, right, yeah. My zip code. Okay, so this is my expired credit card number, just for the record. Okay, 7. How many people got 7? Okay. 9. 11. All 16 or 17? Okay. Okay, nice. All right. So at some level, now we're outliers here, but this comes from the number of things that you can hold in your short-term memory. This is George Miller's magic number, 7 plus or minus 2. This is one standard deviation, so you can figure out how deviant you are. But the bottom line is basically this is how our cognitive structures work, is that you can hold 7 plus or minus 2 things in your short-term memory. Wayne Gretzky actually holds more, interestingly enough. It's kind of interesting. But the question is that it? Let's try another one real quick. Here's another one, 1776-1865-1945-2010. Okay, I won't even give you as long on this one. I want you to think about it, write it down or whatnot. You don't even have to write it down. Well, you can write it down if you want. And the question then is how'd you do? Okay, how many of you got all 16? Okay, I consider that excellent instruction. So, of course, something did change. What is it that changed? Association with years or dates. So, in fact, there are no longer 16 items here. There are 4 items. Okay, this is a phenomenon known as chunking. And you might ask whether chunking works for anything. I could ask you to memorize these 18 letters, or these 18 letters, or these 18 letters. All right. So how we build on what it is that people know. I mean, I can go give this talk. Well, actually, I could give this talk probably anywhere in the world, and people would know those dates in the United States. But if I gave you Canadian Independence Day, it wouldn't help so much. Well, except for the Canucks, right? But the point here is that by actively engaging students and building on what they know in our classrooms, these are those data that we saw before. These were the traditional classes, and these are the interactive, self-described interactive learning engagement classes. And you'll notice 2 things from this plot. One is just about any form of interactive engagement here is as good as the best form of traditional lecture or dissemination of information. And the other thing to notice is there's a huge variance here, broad standard deviation in this. And this is actually, in fact, what I'm trying to investigate. So, for instance, in our introductory physics classes, we find that all of our classes are interactive. They have clickers. And some of our recitation sections in introductory physics are traditional, and they have learning games that always end up in this band. And some of them employ these research-based materials called tutorials, where students are working through sense-making, arguing with each other and justifying. And the instructor is the guide on the side, or the coach, rather than the sage on the stage. And we find these learning games are all over on the higher end here. So I want to just spend a couple of minutes piecing out my work and why it is that this is important. So this is my theoretical frame and bias. This is the work that I do here, and tell you a little bit about this. So I focus on contextual constructivism, and the only reason I include jargon here is so people think I'm important. But it builds on this idea of constructing idea and holding relevant the idea of context. That tools mediate our understanding of cognitive processes, and context shape how we might use these tools, and I'll tell you what I mean by that. The first idea is that tools allow for thought. So for those of you trying to memorize something, much easier if you had a pencil and were writing it down. Okay? But here's a story of another way of thinking about that. This is from actually one of my postdoc advisors, Andy DeSessa, in his book Changing Minds. Galileo is a genius, and at the turn of the 17th century in his Discourse on the Sciences, he wrote, if a moving particle carried at a uniformly constant speed traverses 2 distances, then the time interval required are to each other in the ratio of their distances, followed by a 2-page proof. Now the language is a little bit arcane, but let's talk a little bit about what we mean. If you say that distance equals rate times time, and an object carried at uniform speed, a uniform rate, travels 2 distances here, you can simply divide them, cross them out, and you find that their time interval are to each other in the ratio of their distances. Right? That makes sense? Anybody worried about physics there? Okay, sweet. Now, there are a couple of reasons why I was able to do this. Now, Galileo's a genius. All right? Took him 2 pages to do. Why is it that I can get 6th graders to do this? Actually, I can get 1st graders to do this. Right? Well, why is that? Ah, I am using symbols. And in fact, the formalized version of symbols, and this is actually, strictly speaking, correct. The argument is algebra had not been invented yet. In fact, algebra had been, but not in a symbolic form, arguably. All right? And certainly, algebra wasn't around in common use to manipulate this way. And if you want a challenge to yourself, and you want to act like a genius, prove this geometrically. Okay, so that's one way of thinking about it. So having new symbols or new ways of talking, new language, allows for new ways of thinking. And now I can have 6th graders or 1st graders or college students even have purview or access to what had been only the landscape of geniuses before. This is the important things about new tools and technologies. Here's another one. If I want to divide, 7,960 by 10, pretty, well, I would say easy. And if I wanted to divide that same number by 16, the answer is that it's harder. And now why is that harder? And you might say, oh, I know, it's because of our decimal system. But you can imagine that our decimal system comes around because of our biology, the way we think about things, the tools that we have at our fingertips, or in this case, in our fingertips. But imagine a different world. Imagine a world where we counted in hexadecimal. All of a sudden, this becomes a remarkably simple calculation. And there are 2 shifts. I won't get into this in detail. There are 2 different tools. There's a basis set, basis and the representational form of that basis set that we have. So I will, boy, I have a bunch of stuff that I could share because context is really important to me, and that's what I talk about. I'll just do one here because what the heck. And then we'll kind of wrap up shortly and take questions. The meaning of these tools, I've sort of given an allusion to this already, is both biological, say our fingers and our representation, but we as creatures are wired to see things. This is known as Shepard's tables. So there's a short side and a long side on each table, right? Which long side is longer? That is, which of these 2 sides, these blue lines, is longer? No, I actually have to be the one on the left, right? So let's make sure here. It always depends on the projector here. Is this mind-boggling at all to anyone? In fact, the blue lines and the red lines are the same length? Huh. The real challenge actually is not that they're the same length. The real challenge would be to build these tables because they're physically impossible. Our brain is constructing a 3-dimensional image out of something that's now been flattened here in 2 dimensions, but it's an optical illusion. But this is known as Shepard's tables. We're wired to see things in particular ways. But also the meaning of tools then is also cultural here. So this is a great example from my colleague, friend Corinne Minogue, Oregon. But if I have a function t of xy that's equal to a constant times the quantity x squared plus y squared, what is t of r theta? It's not a trick question. What? Yeah? Okay, CR squared. Anything else? Anyone? You're in math? No? What? Ah! C times r squared plus theta squared. Of course. So physicists invariably say that it's CR squared. Mathematicians invariably say that it's C times the quantity r squared plus theta squared because, you're taking the first index and substituting it for the first object and taking the second. Right? Well, that's what I told you to do. Right? And then a physicist says, you can't add meter squared and radian squared. And a mathematician says, what's a meter? Right? There's all sorts of implicit or cultural knowledge sort of embedded within these systems. And this is, in fact, what we try to unpack. And when I create educational environments, in fact, and when we think about this, I think about the many different layers or cultures or contexts that we embed within this. So a student actually engages and uses some sorts of tools, and that can be drawing or pictures of the textbook or the professor in trying to understand some sort of concept. Maybe they're actual light bulbs in trying to solve that previous problem. Okay, but that particular task, where we're engaged in using two-dimensional drawing to make sense of a concept like vectors, takes on different meaning if I'm inside a class, like tutorials, or I've got a flight plan. Right? But even that class, these tutorials may be different if it's part of Physics 1, right, for, you know, physicists and engineers, or pre-med. They take the activity to mean different things because, in fact, the grades mean different things, interestingly enough. And these, we can keep layering out to the departmental level and sort of culture and community. So this is, in fact, what I do in my research, and I won't bore you with all of this, but I look at across the scale of individual course and departmental on the one hand, and I also talk about these different kinds of themes or artifacts. So these are, you know, tools that we use, and whether those are representations or physical objects like clickers or computer simulations. But then there are also, those help us shape, you know, our understanding of things. But then there are also these practices and rules about how we get to use these tools. But then, like talking inside a classroom if I'm using clickers, right? But then there are also norms about, rules about how we use those rules. Like, you're not supposed to talk in a lecture. So students come in and think differently about that. So each largely the outside drives the inside more than vice versa, but they constitute one another. And if I've got projects in all of these different areas, whether it's development of computer simulations or the development of these attitudes and beliefs, those fit over here in the norms. What am I supposed to be doing when I'm in my class? Or course practices and clickers here. In fact, so given that I'm supposed to be doing a lot, I'm doing a lot. So I'm going to skip a little bit about our studies of lower division as well as informal science, but happy to answer questions about that. And I will wrap up just very briefly here by talking about ways to be involved and what is it that you might think. And so, I mean, there are two explicit, well, related to these areas. There are many more ways to be involved, but here are two explicit ones that I'm involved in. One is that we have, they're preparing future faculty programs across campus. And it's not saying that you have to plan on being a future faculty member to participate, but the graduate teaching program runs a number of fabulous programs on campus as well as the faculty teaching excellent programs. And we have a new program preparing future scientists and now engineers that's running out of our department that's specifically designed to support you all, which is to say you all may be, you know, really well educated on your bench work if you're building lasers or writing on your pieces of paper if you're mathematicians. Just kidding. But we don't always talk about broader issues like teaching practice or curricular development or your professional roles. What does it mean to go out and work in industry? Or, I mean, I know more of that's happening in this particular group, which is fabulous. Or the broader context. What is the institutional context that this sits in, or policy? And we have a program that actually spans across each of these arenas. And this is a sort of every 2 or 3 week seminar series that runs over lunch. We feed you lunch, and it is designed and run by graduate students, and then we support it with faculty speakers to come in. And so this is a program that we are trying to announce to the COSI community. Another program that we have running, which is increasing, is this Partnerships in Informal Science Education in the Community. This is, in fact, where we go and teach engineering projects to youth in a variety of different after-school programs, whether it's at schools after school or in community centers, traditionally for underrepresented populations in these environments. They're loads of fun to engage in. I mean, you know, so there's university educators coming with community centers, such as all housing and urban development centers have to have, or low-income housing centers have to have an education program, but they don't ever do science because they don't have scientists. So we run the Junior Scientist League. They're engineers. It's, in fact, we lie to them and tell them they're doing science, so they really build robots and stuff like that. And they also make movies about what they're doing with stop-action motion animation. They're very excited about this, and it, actually, to be honest, whenever I get sick of the university, I get to go play Lego after school. So I will, in some sense, conclude where I started here, which is to say, in terms of our educational practice, we know that actively engaging people is important. What people know affects what they learn. And then the context, and this happens both within a local context, how I frame a particular problem, question, as well as the educational environment. So children who are otherwise told you can't do science because you're from a community that's never done science, or your parents have never talked about science, or you represent some population that has strong cultural images that say you can't do science. We change that context and say, wait a sec, you're the scientific leaders, and help us engage. So all the way out to the broader sense of context and large-scale culture. So I think what I will say is that'll be it. I'm happy to talk to you about anything else along the way. I think there's great opportunity for you as you are agents in your own educational system. So I conclude with this, as well as maybe my email address, because I'm happy to chat with you about anything along the way through your career. So thank you very much. I'll take some questions.
Questions? Comments?
Yeah.
So I went to my undergraduate here at CU.
Right?
And teachers who were really into the clicker and the active engagement, they drove me nuts. And the reason for this is I was actually first generation college, relatively low income, and I worked to put myself through school.
Right.
And I had to work.
Right.
And sometimes shifts overlapped class. And every
Right.
class I had that had a clicker, I got a C. And every class I had that didn't have a clicker, usually I did pretty good.
Right.
And I'm wondering if there's anything being done, or if this is off the radar, of making a place like CU Boulder more accessible to low-income students, and if there's any way to overlap that with this active engagement educational model.
Okay. Fabulous question, which I'll repeat briefly for the sake of the tape, I think, or anybody else, so that I can answer the question that I wanted to answer rather than the question you asked. No, so this interactive engagement and the clickers, at some level, demands of you participation and performance that otherwise our cultural systems don't allow you to engage in because you have to work. And so you did well in courses that didn't have clickers and not as well for courses that, you know, counted that as part of your grade and participation maybe even as part of your grade. Or so I don't know. I mean, one way is that courses that use clickers might have had a different educational goal than courses that didn't use clickers. So these are confounding variables, and why we want to sort of tease these apart carefully. So it might be that the traditional classes are the ones that, you know, where you solve back of the chapter problems and you go in and you take your midterm and your final and that's it. Your grade depends on that. Much more mimic the educational environments that you'd been in previously that we can show are good at certain forms of learning but are limited to those forms of learning, like solving that traditional circuits problem. And once we sort of expand beyond that to say, all right, what's the conceptual underpinning that's going on here, what classes that I would argue are more demanding and inclusive of the broad array of learning goals, those in fact, so it might be this issue of learning goals are different in those two different environments. And the problem is that these learning goals that we have that are enriched not only demand more participation of you, but in fact, that's what learning is. I mean, one argument about what the definition of learning is learning is participation in different environments. That's a fairly radical view of what learning is, as opposed to performing well on a bubble sheet. But I would argue probably more authentic. No employer is going to have you come in, at least I really hope no employer is going to have you come in and bubble in sheets for your job. Okay. That's, right. There you go. Okay. So in fact, right. I mean, and those are great. I mean, if there are environments that are prescriptive, that are actually labor-oriented, where you do some that are totally prescriptive environments, we actually know how to do that, the new generation of factory workers. But that's not where our economy is going. We want students to be actually the problem solvers of the future. We want them, in fact, to be the questioners of the future. So I'll give you a strong answer and a weak answer. My strong answer is that our educational system should invest in you by providing you the financial resources necessary so that you can spend your full attention here at the university and focus on that. A quality university education demands your attention. You don't go to grad school, you know, especially in engineering. I mean, you're all in this program. You all have, you know, I guess some level of fellowship. We do that on purpose so that you can focus your attention in ways that are necessary now. Now, the modern university system or modern college system doesn't currently afford that. That's not the real world. I am pleased to see the university moving in that direction and increasing the level of financial assistance. That's part of this sort of more independent movement about our tuition structure, and I think we should go there. If you wanted to get really radical, so that's a strong answer. It's partly outside the box about what could happen is, you know, stronger financial aid so that you didn't have to work, so that you could go to these classes and fully participate and fully learn in these environments. The best answer would be, to me, is if all college were free. There are plenty of, you know, places where that's true. Most of Europe is basically like that, And I think that's worthwhile. It also shifts our cultural attention to that. That's at some level, that becomes political because that's in the realm of not immediately possible here. The softer or weaker answer to this is people are also attending to say, how is it that we can still engage in these practices, the interactive engagement, the building on what students already know, the attention to context in ways that are asynchronous and allow you to do it offline. And there is a increasing attention to distance education and distance learning. I spend a lot of time thinking about this. I think that there is tremendous potential. I was just consulting for Paul Allen's company. This is interesting. He wants to create the textbook of the future where you just ask the textbook a question and it'll give you all the tutoring you need in order to answer it. It's sort of like science fiction, because it is. And that's in fact where he got the idea, was the Encyclopedia of Everything for those who are really old. If anybody read Diamond Age, this is also that book in Diamond Age. A mixed opinion about this. So the point is that yes, we can do that. There are folks at Minds who are working on distance education in really clever ways. Can you embody these clicker questions on there? Can you videotape and sort of pause and give the right information about, lecture is valuable, and in providing information, and then you can do the processing at the right time in that. And we can embed that within these sort of asynchronous learning environments. The danger to me about this, though, is that education is fundamentally a social act. A lot of that has to do with your turning to your neighbor and negotiating what's going on. And so I want to provide more resources for people to learn, but I don't think we should take the opportunity to pay less for our educational systems and put it all online. And this is one of the big dangers about what's going on in our higher education systems. Maybe beyond where you need to be focusing on right now, but this is one of the big threats in our higher education, is that there's going to be business competition from online systems that don't provide the quality education that we can provide in person, but say that they're doing it. Yes?
Do you have some methods that you use to assess incoming students' misconceptions about the physical world before you actually started your first year physics class?
Yes, sort of two sort of responses. The answer is that this pre-post test, all of these things are given pre. So we have a collection of data about what is it that students know coming into our introductory physics class, in our introductory mechanics and E&M class. And there are conceptual surveys now in just about every area of inquiry. Increasingly, actually, it's happening in engineering where this is happening. And there's a robust scholarship to producing these things. Do we use those to tailor and change our courses? And the answer is not very rapidly or responsively. So we could do better, but it's expensive to change a class, and it's hard to do it dynamically along the way. So the answer is yes and no. We do assess what it is that, what are the ideas that students have coming into class. And in our introductory sequence, they're fairly stable. We actually have a pretty darn good idea now about what students come in to our introductory courses, at least in physics, are thinking about, because we've been doing it for 5 or 10 years now, and we know that students think about things in particular ways and are are adapting our curricula to address that. The other thing is, though, that the word misconceptions is a tricky word. So it's not entirely clear that students have robust ideas about what's going on coming into our classes. And so if you ask them for an answer, they'll give you an answer. But that doesn't mean they have a full-fledged sort of conceptual framework and domain behind that. It might just be that they were activating these sort of more fine-grained resources, like, heavier objects fall faster. Well, I mean, sort of, but you can't really attribute that to a whole conceptual framework or robustness, to that. And so so I'm a little bit cautious about the pretest. But this whole idea of attending to what students know coming in is very important, and we're doing that more and more. Right? Very valuable.
I got one, maybe the difference between engineering and physics education.
Great.
I love the hidden curriculum of original speakers. It's wonderful.
Thank you.
I struggle in my engineering classes to teach students those conceptual fundamental basics, and they resist like hell.
Right.
Because as engineers, they really know how to solve the problem in the back of the book.
Right.
I'm not sure they're wrong if I'm training them to solve problems, and that their idea is I don't want to know what to buy the box. I want to know how the box works because I build stuff out of boxes. So I, as a professor, am fascinated by the fundamentals.
Yes.
We as practicing engineers, not so much. And I'm curious what you think about that.
That's a great question. For the tape, right, the question is, I want to tease out, though, the distinction between conceptual foundations and fundamentals or foundational ideas and basics. So I think, in fact, we probably teach physics wrong, which we start with, all right, here are Newton's laws, and here's all the different applications of Newton's laws and rotational coordinate system and an angled coordinate system, and then eventually maybe we get to some application later on. But in fact, and this goes back to the, for children and teaching, kids, why kids are natural born engineers. They start with the phenomena, the objects that are going on, and then say, all right, what are the pieces that I need to know in order to solve this, to make this widget better along the way? And, at some level we call that engineering. To me, I just call that good scholarship, which is to know what it is and why you're doing it. I think that engineers actually do a darn good job. I love ITL here. All right. To me, that is all about conceptual framing and starting with the boxes and saying, what is it that I can do? Now, knowing that I want to build, say, this strobe light, and then as a result of that, I need to know some fundamental principles, say, about RC time constant, or I use this as an opportunity to teach algebra to 6th graders because they want to build a strobe light, and now all of a sudden, this bit of knowledge becomes an instrumental tool for them to solve a problem that they have that's relevant to them and out there. And so I think where we run the risk is that if we only make better problem solvers who can calculate the electric circuits or the current in the electric circuit, we might do a decent job of that right now or back of the chapter problems. But what ends up happening is then they become really good at solving other people's problems. And I started to shift. I used to say my job is to make better problem solvers. And now my job actually I frame as I try to make better questioners. Because being able to ask the question to me is the critically important point. And then, because a sophisticated question is framed in a way that you know that you can make progress on it by applying the problem solving skills, both the conceptual, I'm not trying to highlight conceptual over the traditional algorithmic, but rather to marry the two of those so that they're joined. And I bet this is what actually happens in the best engineering courses right now. And students recognize that these things are valuable. I mean, I'm going to go back to the point here is solving back to the chapter problems isn't necessarily any different than bubbling in a sheet. And there are plenty of students who we've taught, your job is to get the right answer and we're going to give you a cookie for doing that or whatever it is. But I think that's cheating our students in terms of, frankly, their human potential and certainly their workforce potential by playing to that lowest common denominator rather than elevating it.
My observation is that motivation has the largest difference in kind of the form of like that. And I find that there are two different forms of it. One's encouraging under excitement, the other is, I call it the carrot and stick.
Right.
And both of them seem to have an effect. I'm curious as your comment.
Absolutely. So motivation is, if you ask any practicing teacher or any of us who have spent time teaching, probably it's always one of the top 10 things or top 5 things, and usually the number 1 thing that comes up. And the problem is that motivation is such a difficult concept to turn into a scholarly model, or that we're just dipping our toe into that. And we're doing that actually now in our group, and we're looking at questions of self-efficacy, which is the belief in your ability to do something, which is only a small part of it, because it's wrapped up in identity, which is wrapped up in culture, which is wrapped up in the nature of the discipline. I mean, it's just a hard problem. I mean, it's a really nonlinear problem. And and we don't even know what all the factors are that go into it. Critically important, but we do know that there's extrinsic motivation, intrinsic motivation. This is very naive characterization about it. And then there's positive reinforcement and negative reinforcement, the carrot and the stick along the way. And you can create, the problem, invariably the problem in education is when you ask a sophisticated question like this, you always get the same darn answer, which is, well, it depends, right? So I can construct environments that by and large have negative reinforcement that are very productive and very good. All right, along some dimensions, say, or positive reinforcements. And the answer is it's going to be a bit of both. One of the problems that we find, for instance, in these tutorials that we have in the recitation sections, I didn't show you, but it's small group work focused on student learning. Along the way, we never answer students' questions in the class. We always answer a question with a question, which drives students bonkers. But it teaches them to reason and ask the right kinds of questions. We know that it's productive to their learning, but it also teaches them to hate that process. Okay, and we don't want to do that. My colleague Mike Dubson, his first credo, borrows from medicine, is first do no harm, right? So I think that the answer is yes. We want, the bottom line, and we know this from a variety of different work, is that you hold people to tremendously high expectations, all right? Set the bar out there, make it explicit, and then provide people the resources necessary to achieve those expectations and the expectation that they achieve those. And that's a mix of carrot and stick, no question about it in that sense. But in terms of educational practice, those are the things that seem to work, that take, and whether that's kids who have never gone to college before, or from families who have never gone to college before, to kids, who have all the way been along high achieving. And there's sort of a great opportunity there. Maybe it's not a very satisfying answer, but I have a colleague who says, look, if you want your students to learn it, you have to test them on it. That's a stick. And the truth is, that's a great way of externalizing and sharing a common culture. The downside is students are always stressed about it, or, for instance, we find from our gender research that, in fact, stereotype threat, which is a sort of great area of research I'm happy to talk to you about, is something unrelated to sort of individual capacity or capability, but demonstrates that whichever stereotype you're afraid of being, and we're all members of stereotype groups, but in physics we find that women perform less well on exams than men, largely because of the psychological factor, not because they know less physics. We can demonstrate this time and time again. And so the bottom line is, how is it that our educational environments are measuring and giving us what we want, and what are the tools that we can use to motivate people? Bottom line, I'm a positive guy. I like to give all my students hugs, let them know that they can achieve that. But it is true. I think that there's this sort of, I don't know that I would characterize it as carrot and stick so much as demanding excellence of all of my students, providing them the resources to do that, and working with them to do that. It's also a little bit, hippie and new agey of me to say that all of my students can achieve, because I do have students coming into my class who fail, right?
Well, one time that failed, largely because it didn't do the work.
Right. Right. But if people are serious about engaging in the environment, or have the resources, or frankly have the financial support to come, I think we want to improve our educational system. Quit making students work half-time or full-time jobs to come to an undergraduate degree. That's absurd. If we want our students to work 3 hours outside of class for every hour in class, and they're taking 20 credit hours, so they're 20 hours at the school, and then another 60 hours, what it takes to really learn this material, how are you going to work a half-time or a full-time job? That's big.
I agree with you on that, and I can give you examples that fit well into the case that just was raised here.
Yeah, yeah.
And cases where, at least in one case, where I succeeded in solving that problem.
Right, and I think the point that I would close with actually is that invariably what matters to individuals are other individuals. We can all, it really does in our environment, comes down to one-on-one interaction all the time, as well as we have new ways of thinking. We have a scholarship in the way that we think about education, and new tools that are based on this underpinning model of student learning that are effective, that allow us to sort of move around the edges and the constraints in our educational system so that we can provide better education for our students. And that's starting to happen. And you should all be proud too that, CU is heralded as a national leader in our reform efforts in science, technology, engineering, and math education. It's not accidental that our chancellor was just brought to the White House, and it's because of the reforms that are going on in STEM education here in Colorado.
Thank you.